Hello guys, and welcome in this new recording. I am still working on this tree designer tool, but today I would like to make another quick video recording on the equirectangular projection or environment mapping process if you want. I had already implemented a previous example, and when I say that I have implemented the previous example, I mean that I took this example code from the WebGPU native examples repository and I actually adapted that to my own WebGPU engine, and here is the shader which was used in that old example. It's actually a bit complex, and when I was implementing that I was not really understanding most of it. I'm still not quite sure to understand everything in fact. But if you read this code, it's actually a bit complex, and now that I have a better understanding of how you're supposed to deal with this projection, I decided to revisit this and try to provide my own simplified implementation. So let's try to run the old example code. This is what the equirectangular environment mapping looked like. It was working, but in fact you have to provide the mouse position to do the computation, and it seems a bit jerky. So maybe there's something wrong in the way I built this, but still. And now here is the updated version in the tree designer tool. So we have the tree in the middle, sure, but then you see that it seems a lot smoother, and still the display is okay. So now let's see what is the implementation we have for the shader part. This is a vertex shader and this is a fragment shader. So it's significantly shorter and simpler than the previous version of it. So now let's start to understand a bit more what we're doing exactly in the shader. First, the equirectangular projection itself is pretty simple if you think about it. The idea is really just to have this rectangular texture, and on there you have a direct mapping of lat long coordinates onto the texture, which means that when you get close to the poles, the display is pretty distorted. And if you get on the last line here, you're really actually displaying a single point on your sphere when you do the mapping, but that's really not a concern from our perspective. The question then is, how do you apply this texture on the sphere if you assume that you have a kind of sphere box around the player location or your virtual world? And really, if you need to do that, all you really need to have is your camera, which you consider to be at the center point to display the sphere, and your camera frustum is going to give you, well, 4 directions for the 4 corners of that frustum. And when you have those 4 corners, you basically know all you need to know to figure out what you need to display on the sphere. I know that saying like that it sounds a bit tricky and unclear, but maybe we should have a look at the code itself and it should be easier to follow from there. So what we're doing here is we start with this vertex shader, and for the vertex all we have is the vertex ID when you receive that as input. So what we use, for instance, in the tree designer here is this part of the code where you're sending 6 vertices. You need to have access to the camera data because you will need the inverse projection matrix and the inverse view matrix. We'll get back to this point in a moment. We also need a sampler because you have a texture and you need to do sampling on that texture. The texture itself is the equirectangular texture. So in this case I'm using the circus backstage, and this is the equirectangular texture if you load it from the disk. Now first, on the sampler part, it seems logical that you would like to use linear sampling because otherwise you would do nearest sampling, and if you try that, well, you will get some squarish effect on the display of the sphere. So definitely you need linear. Then there is a case, in fact, when you're doing the display on this texture on the sphere, where you're going to reach the very limit corner either on the right side or the left side, and when you do that you still want to be able to do linear sampling and use the information that you have on the other side of the texture to do the mixing of your, well, current location. So that's why I think using repeat mode in this case is also the most appropriate solution. And with only those 3 bindings, we have all we need to perform the equirectangular mapping. So in the shader, this is where we receive the data. We have the camera uniform data first, then the sampler itself, and then the texture 2D. As I said, we're going to use the vertex ID to figure out what are the UV coordinates corresponding to a full screen align quad. So the coordinates here would go from 0 to 1 to cover the full camera frustum. Next, we use those coordinates to generate a clip space position. So this is going from -1 to 1 in both the X and Y direction, and we use 1 for the Z to mean that you have the position at the far plane to ensure that the sphere itself will be displayed behind everything else in the scene, and that's directly the position you want to use. And next, the interesting part is here. Once you have this position in clipping space, you can use a projection matrix to inverse this and get your position in the camera space. So this is exactly what we do here. We use the inverse projection matrix, we use the position that we have computed, and then we get the camera space point corresponding to that projected location. Once you have this camera space point, you're going to change your perspective, and that point is actually the far point corresponding to one of the 4 corners of the camera frustum. But you can also consider that this is giving you the direction of that point from the camera location, and given this direction of the point, you can then apply the view inverse matrix to get the corresponding direction in the world space. This is what we do on the next line, and in the end what we get here, the view direction, is your camera frustum corner direction in the world space. So from there you can imagine that you have your world frame, where I guess it depends then on the convention that you're using, but in my case I'm using Z always forward, Y is actually down, and X is a right vector. And so given this frame, you now have those 4 vectors corresponding to the camera frustum, and this is really in the world space. So you're going to forward this information then to the fragment shader, and when you reach the fragment shader, you're going to normalize this vector again because it's going to be interpolated, so the length of the vector is going to change a little bit. And from there, you simply consider that you're going to compute lat long coordinate with this direction given in the world frame. So as I said, for me, Y is down, so up is actually -Y, and if you use simply the value that you have here on -Y, that's going to allow you to compute the latitude angle, and the latitude angle is going to be between minus pi divided by 2 to pi divided by 2, and you're going to normalize this latitude value between -1 and 1. That's why I'm actually multiplying here by 2 dividing my pi. Next, you have the longitude coordinate, and for that you're going to use the X and Z component of your view direction, and you can very easily compute using arctan to a value between -pi and pi. Again, you normalize that, so you divide by pi to get a value between -1 and 1. Now your latitude and longitude are between -1 and 1, but if you want to turn that into texture coordinate, you need to multiply that by 0.5 and offset by 0.5 also. And that's it. With that, you actually have coordinates that you can use to sample the equirectangular texture. So that's what we do on the next line here, and that's all you need to get the display that we have shown just before, and which looks exactly like that. No issue at the top or north pole, or at the bottom the south pole of the texture, and everything seems exactly the same as in the previous example, except that the code is simpler and we don't have any jerky movement anymore due to the mouse location input, so we actually need a lot less inputs. One last thing I would like to mention here is one issue on which I spent quite a lot of time to figure out how to fix it. It's here when you're about to sample the texture. Initially I was rather doing this, so using texture sample to do the sampling of the texture, and if you do that, everything would look almost the same except for this line here. And also, yeah, actually the display here is not good. You see that there's a weird, I don't know, filtering occurring. And at the top you also have that a little circle here. And this line where you have a weird color display. And I spent a lot of time trying to figure out what is going wrong here. And the thing is, really, when you use texture sample, the API or driver in the backend is going to use the derivatives of your UV coordinates to figure out how to do the linear interpolation between multiple texels. And in this case, this is working fine everywhere except on this line where you're going to cross between the U coordinate value 0 and 1. So you have a discontinuity at this point. So this means that your computation of the derivatives is going to be wrong, and I guess this is why it's going to mess up the display at this specific line location. So you really need to avoid using those derivatives, and instead, to do that properly, you need to specify that you want to use the level 0 of the texture. There is only one level actually for this texture, but you need to specify it anyway. Now, in case this could be of interest to anyone, I'm also adding a very small article on my technical notes here to provide the complete code that I currently use for this WGSL shader. And yeah, feel free to use that, modify as you need, and so on. So this is it, guys, concerning this equirectangular environment mapping update. I hope you learned something, or you found that somewhat interesting at least, and from there I will continue working on my tree designer tool, and I will let you know when I have another recording available on that one. So see you next time, bye bye.